Continuing with question number 2 of RACE-3 of the Secureum Bootcamp, it says, given that lower indexed numbered crypto-SAFU NFTs have rarer traits and are considered more valuable, as commented in _mint, the implementation of in-Secureum NFT is susceptible to the following exploits. So that's quite a long sentence. So we have an in-Secureum NFT contract, and within this contract we are managing crypto-SAFU NFTs. Each NFT has its own index or number or just a unique identifier that you use. For example, every time you want to transfer an NFT that you own, you use the unique identifier of that NFT. And it says here that the lower this number, the lower this unique identifier is, the more valuable these NFTs are. We can also see this in the _mint function that was mentioned, because it says here, lower index numbered NFTs have rare traits and may be considered as more valuable by buyers. Therefore, randomize. We can see here that the ID isn't just an increment, but it is actually randomized every time the mint function is called. Now the problem is that randomness is really hard on chain, and there are possible exploits here, and some of them are that buyers can repeatedly mint and revert until they receive the desired NFT. So if we deploy a smart contract which calls the mint function, pays the price it has to pay for minting, and then it receives an NFT, and then it could just check, is this the NFT that I wanted? And if not, well, revert. Revert means everything is undone, the NFT is given back, or rather it is as if it had never been minted in the first place, and as well our funds that we sent to buy the NFT are returned to us as if we had never sent them. This would still be quite expensive gas-wise, because we would have to pay all of the gas up to the point of the revert, but that is certainly something that we could do to make sure that we receive a valuable NFT, that we can avoid paying money for an NFT that we didn't actually want. Now, how could we prevent that? The reliable and easy way to prevent this is basically to check whether the message sender, so the caller of the function, of the mint function, is equal to the tx.origin. tx.origin is the signer, is the EOA account that signed the current transaction. So since tx.origin is guaranteed to be an EOA account, and if it matches, if it is the same as the message sender, we can be sure that what called us, what triggered the mint function, is definitely not a smart contract, basically. So unless this mint function has this check, we can say that A is going to be true. Then we have B. B says buyers can generate addresses to mint until they receive desired NFT. So it says that buyers could just keep generating addresses and, well, until they just end up with a very valuable NFT, because this buyer address influences the randomness that is used to determine the ID. And option number C is similar, because it says miners can manipulate block.timestamp to facilitate mining of desired NFT. So here it would also be that miners, when they mine a block, they could choose, I think it was plus minus 15 seconds. They have quite a bit they have some leverage over the block.timestamp to manipulate it and make it whatever they want, but only within this valid range. And they could also make sure that they select a block.timestamp where they would receive a more valuable index, basically. But as you hopefully know, we have had the merge. We are now proof of stake in Ethereum. So there are no longer miners, we have validators now. And this also changed how block.timestamp works. Because before we had this, miners could just, not quite arbitrarily, but they could pick any block.timestamp as long as it was within a certain valid range of parameters. And since proof of stake, these block.timestamps are basically predetermined. Like, they're based on slots. Each slot has its predetermined timestamp, which is always 12 seconds basically. So the block.timestamp will always be a multiple of 12 seconds. Maybe once or twice every month it happens that a slot is skipped because someone in the system didn't produce a slot. It shouldn't happen that often, but when it happens, maybe one of those block.timestamps is skipped, and then there would be like 24 seconds difference between the previous block and the current block. But in the usual case, it would always be 12 seconds, 12 seconds, 12 seconds. So as it is now, it would no longer be possible, but this quiz was created before the merge happened. So we will just continue with this assumption that we still have miners. So let's first look for A, whether there is actually a check preventing smart contracts from calling the minting function. We can see here that mint, the external mint function, checks whether the sale is already started, whether the sale limit has been reached, whether sufficient funds have been sent. It checks, we actually have an is-contract check here. But this is-contract check is not to make sure that the caller, that the buyer isn't a smart contract. This actually just checks whether the caller is a smart contract to make sure that if it is, that the on ERC 721 received callback is called. So that basically tells us that it is even wanted that the minting function is called by smart contracts. Now, could this is-contract function, this helper function, be used to prevent contracts from calling? Well, you could try, but it wouldn't be very smart, because what it does is that it checks the address size. So it checks the address size of the receiver of the NFT, and if the size of the code at the address is larger than 0, then it must be a contract. But that's not always the case, because if a contract is currently constructing, if it's still in its initialization phase, in its construction phase, so the constructor is currently being executed, that means that the code resulting from this initialization isn't stored at that address yet. So we could use the constructor to call the minting function, and the minting function, if it doesn't return the result, the NFT that we want, we could then revert within the constructor to prevent receiving the NFT that we didn't want. So checking the code size is not going to help prevent this vector, but it isn't even used this way. There is nothing here preventing smart contracts from calling the mint function. Therefore, A is definitely a way to exploit this, even though it's not a very efficient way, because it will still cost quite a bit of gas to do this. Then B and C, can the buyer address and the block.timestamp manipulate the randomness or influence the randomness? Now, as you remember, we have the random index function that determines the unique identifier of the NFT, and it is determined from the result of a hash. So are hashes random? Are hashes a good source of randomness? And there it depends. It depends how you use them, what you use them for. Because if you cannot predict the result of a hash, you cannot predict, if you give it some input, if you give some input to the hash, you cannot predict what the output will be. If it is a good hash, if it is a good hashing algorithm, you cannot predict the output. But if you know the inputs and you know how to produce the hash, you could just produce the hash before it happens here. So if we know all of the inputs of this catcheck call, then we could just locally pre-calculate what the hash result will be, and therefore it is no longer really random, because it is predictable randomness basically. So that's not a very good source of randomness, especially in blockchain, because we can always simulate what the next block will do basically. Now, what else do we have here? We have a nonce, which you can see there. this nonce is increased by 1 every time random index is called. Then we have a message sender, which is the receiver or the buyer. And one of the options was that the buyer would be able to influence using their address. So indeed, if the buyer would just generate a whole bunch of addresses and they would test it against this hash, they might be able to find that one of these addresses indeed results in a hash that produces a very valuable index. So yes, B is indeed correct. And then we also have block difficulty and block timestamp. And block timestamp was the last option that we had in this question. So indeed, miners can also manipulate the randomness using block.timestamp. So the easiest way to exploit this, or not the easiest, the most efficient way to exploit this, now that we have validators, we can predict what the next block timestamp will be. We have a block difficulty that will most likely not change until the next block, or we can already predict what it will be, better to say it that way. We can predict what the nonce will be because we can just check it based on the current state of the contract on chain. And we can also generate lots of different message senders so that one of them might actually result in an index that is valuable. So we can do all of this, we can do these entire calculations off-chain and only send a request, send a transaction to Mint if we know beforehand that with these inputs it will result in a valuable NFT. So for question 2, we have seen that randomness is pretty hard on chain and that A, B and C are correct in this case.